Hi, I'm Thomas, and this is the bonus lecture for my lecture series on algorithms engineering. And today we'll look some more at sorting. So what we're going to do is we're going to do sample sort, which is an algorithm from the 70s, and it's not so much algorithms engineering at this point. Then what we'll do is we'll have some observations about sorting on modern hardware, and some of these are from Sandels and Winkel from their 2004 paper, Superscalar Sample Sort. And then we'll look at what they do with these observations to make a practically fast sorting algorithm on, let's say, modern hardware. Okay, so first, let's do sample sort. And it's a divide and conquer algorithm. So quick sort is, of course, a divide and conquer algorithm. And it splits the array in two parts based on a single pivot. And let's say I get very lucky and I pick 4 as my pivot. So we're splitting the array into those elements that are less equal 4 and strictly larger than 4. Or maybe I put the 4 on the other side, doesn't really matter for our argument here. And then it looks like this, and I can recurse on both sides. Now there's a different idea called bucket sort, which is to say that we split the array in many parts based on fixed thresholds. So if we know that we only have a few distinct values that could possibly be in our array, then what we could do is we could have a bucket for every distinct value, just count how often each one occurs, and then reconstruct the output array afterwards. You could do this with small integers, for example. But more generally, you could say bucket sort has fixed ranges. You put the input elements into the correct bucket, and then you sort each bucket either recursively with smaller buckets, or you switch to some different algorithm. And the fun part of having many buckets is that I could work on them in parallel, and this is where we're going to get to sample sort, because it comes from multiprocessing research. So the advantage of bucket sort is that it splits into many subproblems faster than quicksort and merge sort do. So if you have very many processors, then you can give work to many of them earlier on in the recursion. But the problem you run into is that you have unpredictable bucket populations. So like you don't really know, depending on what kind of input you get, how many elements are going to end up in each bucket. And this even becomes a memory management problem. One of the things that makes quicksort so good is that partitioning on a single pivot lets us put the small ones to the left and the large ones to the right and have the entire thing be in place. But that's not really going to work for us anymore once we're bucket sort into many buckets. But we'll think about that later. First, let's get to sample sort itself. So the motivation is multiprocessing. We want to divide into many subarrays. The problem for them is not memory management, it's load balancing. They want to give each of their different processors approximately the same amount of work to do. And their solution is to sample the input array to get a good set of splitters for the buckets. Kind of like pivots. For quicksort, we have more of them now. It's like the values where you're going to split between the buckets. To do sample sort, there are two parameters, S, the sample size, and P, for them would be the number of processors, but it's also kind of the number of pivots. To sample sort an array A, what we're going to do is we're going to first sample S elements from the array uniformly at random. It's actually an interesting question how you do that, but we won't get into it. Then what we're going to do is we are going to sort this sample. We do this somehow. S is probably small, so this is fine. But let's actually now add step 1 to the algorithm, which is if you're going to sample almost the entire array, then you should just sort the array using some baseline method rather than doing the sampling. So now we have a sample of the array, and we've sorted it, and now what we're going to do is we're going to pick P of them, evenly spaced in this sorted array, so that might be, for example, the 2 and the 5. And now the idea is that these are statistically probably pretty good splitters that are going to give us probably pretty even buckets. So that's what we do. We partition A into the buckets using P as the splitters, and then recursively we sample sort each of the PI, and then we concatenate all the results. And at some point this is going to get to a base case on line 1 where we would have sampled most of the array, and then we don't, we just sort it with a baseline method. So this is an algorithm from the 70s, and the idea is that you actually send these BI to different processors to work on and then put back together at the end. let's think a little bit about these parameters S and P. Higher P means more buckets, which is a wider split into hopefully smaller buckets. Higher S over P, and this thing is called the oversampling ratio. Higher S over P means we have a more expensive divide step. We look at more data and we have to sort it. But what it does is it lets us expect a better distribution of elements into the buckets. At this point, I would like you to notice that if we pick S equals P, so there's basically no oversampling, then what we're doing is we're picking random pivots. And if S equals P equals 1, then actually what this reduces to is randomized quicksort, which I thought is kind of fun to notice. And one more thing I would like us to think about is what happens if two of these pivots that we pick are equal. Is that a good thing? Is it a bad thing? Well, initially you might say, well, okay, that's actually bad because these buckets are defined left inclusive, right exclusive, so then if you have two pivots that are the same, then that's going to be an empty bucket. However, if you think about it a little bit, and you consider statistically how this might happen, then actually if two pivots are the same, then there's probably a lot of specifically that element in the array, lots of duplicate elements. So if you don't handle it, it's bad. But if you have a special case for that, then what you could do is you could make what the literature calls an equality bucket, where you get all of those elements that have exactly that value, and you don't even need to recurse on it. That's kind of nice, but it's something that you need to handle specifically. But this is really all I wanted to say about sample sort, and now let's switch to